This is the presentation on the concurrence of triangle medians and the centroid by Tony Torres, Matthew McKentz, and William James. This is William James speaking, and in this presentation, we are going to introduce to you the theorem about the centroid of a triangle and prove it for you all. So, let's get started. This theorem states that the three medians of a triangle meet at the centroid, and the centroid of a triangle lies 2/3 of the way along the median from the vertex. In order to understand what any of this means or what we're going to be talking about while proving this, we're first going to need some definitions.
So, in order to understand the statement of the theorem, you first have to know what a median is and also what a centroid is. A median is the line drawn from a vertex of a triangle to the midpoint of the opposite side. Obviously, since there are three vertexes in a triangle, there are three medians in any triangle. So, for example, in the diagram here, AY is the median from vertex A, and it divides the side BC such that BY equals BC. The point where the three medians of a triangle meet is called the centroid, and we will show that they all meet at the same point. We call it G, and also, interestingly, G lies 2/3 of the way along the line from each vertex.
The medial line is the line that connects the two midpoints of two sides. On a triangle, we will call this line XY, and it divides the lines AB and AC in half, essentially. A parallelogram is a quadrilateral in which opposite sides are equal and parallel. This won't be coming in for a while, however, this very basic definition is necessary for the proof that we will be discussing today. Z factor and X factor are what we call alternate interior angles, alternate exterior angles, corresponding angles, and vertical angles. All this is when you have two parallel lines intersected by a transversal, you'll see that certain angles will have the same measurement in degrees. So alternate interior angles will be angles like 3 and 6 or 4 and 5. Alternate exterior angles will be 1 and 8 and 2 and 7. Some examples of vertical angles where two angles are on opposite sides of each other, making an X shape, would be 1 and 4 and 7 and 6. And corresponding angles, where if you were to take that those two parallel lines and just lay them on top of each other, you'd see that the two angles in the same position would have the same measurement, so 1 and 5 and 4 and 8. Now, for alternate interior, exterior, and corresponding angles, that angle measurement only holds true if the two lines are parallel. Vertical angles will always be congruent. There are 4 criteria in proving that triangles are congruent. Congruent meaning that they have the same shape and size. These are side-side-side criteria, side-angle criteria, angle-side-angle criteria, and side-angle-angle criteria. Now, if you have the same measures for these 3 values, then you have 2 congruent shapes. And when we're discussing sides and angles, these are adjacent sides and angles. So if you have side-angle-side criteria, you would have the angle that is adjacent to the angle that is formed by the two sides. Now, when two shapes have the same sort of configuration, but they aren't the same size, they're similar. So if they're the same shape, they're not the same size. For triangles, we can say that there is an algebraic definition of similarity, which is take any two corresponding sides, and they will have the same ratio. So in this example, we have AX over AB is the same as AY over AC, which is the same as xy over bc for the triangles ABC and AXY. This will be used to show our theorem. Now, another way to show similarity is by angle-angle criteria. Because a triangle has 180 degrees and always has 180 degrees, if any two angles are equal, then by definition the third angle must also be equal. Coming back to our original theorem, we need to prove that definition of the centroid, and we will start doing that by using similarity. So we need to show that the triangles XGY and CGB are similar. And we will begin to do this by using the similarity criteria of angle-angle. And we can do that only if we know that XY is parallel to BC. And in order to get to that, we must first discuss a lemma. Now, a lemma is a sort of half-proof. It's something that needs to be said in order to prove an actual proof, but it isn't large enough to worry about itself. This lemma states that if x and y are points on AB and AC in the triangle ABC, if triangle AXY and triangle ABC are similar, then XY is parallel to BC. So this is sort of relating back to our proof that we're trying to prove. In order to start with this lemma, recall that the algebraic definition of similarity is AX over AB is AY over AC is XY over BC. So we'll say that alpha is equal to XB over AB and beta is equal to YC over AC. Then we can sort of say that AX over AB is equal to 1 minus A. Similarly, AY over AC is equal to, well, I said A earlier, and then alpha. AY over AC is 1 minus beta. Greek letters are difficult. So, if XY is parallel to BC, then it follows that alpha is equal to beta. And so now we're going to try and prove that alpha is indeed equal to beta. In order to prove that alpha equals beta, we will look at the triangle ABC. If we use AB as a base, we can see that the triangles ABC and CXB have the same height. And so using the area of the triangle formula, 1/2 base height, we can say that the ratio of areas for CXB over the area of ABC is equal to alpha, or that the area of CXB is equal to alpha times the area of ABC. And this is similar for the triangle BYC is equal to B times the area of ABC. So if alpha equals beta, then the area of BYC is equal to the area of CXB. We still have more of this lemma to prove, so going into it, we need to prove that the two triangles have the same area. And so looking at these two triangles, we see that they have the same base, BC. And knowing the formula for area of a triangle, if they have the same heights, XP and YR respectively, then they'll have the same area. So to prove that XP is equal to YR, we'll notice that they are both perpendicular to BC, since they're heights, and so they're parallel to each other. And so if XP is equal to YR and XP is parallel to YR, then it follows that XYRP, that quadrilateral form there, must be a parallelogram based on the following two facts.
There are two facts about parallelograms that we'll quickly prove in order to finish our proof of the lemma. So the definition of parallelogram is opposite sides parallel, but we want to show the following theorem, that if the opposite sides are equal in length, then then they're also parallel to each other. So this is a simple consequence of congruence. So you simply just draw the line BD here, and then immediately you have side-side-side congruence, and since corresponding parts of congruent triangles are congruent, you can see that angle A is equal to angle B, and if you view BD as a transversal, then you can see that AB is parallel to DC, and similarly for the other one. So ABCD is the parallelogram. The second fact, in fact, follows from the first. So we want to prove that if one pair of opposite sides is both equal in length and parallel, then the quadrilateral is a parallelogram. So we could either use our previous theorem and if we show that we simply draw the line BD here, and then we know that angle A is equal to angle C, and BD is equal to itself, and AB equals CD. So by side angle side, these two triangles are congruent. So we could use the previous fact and say that AD is equal to BC, and we just showed that in the previous slide that if AD equals BC and AB equals DC, then then we have a parallelogram. Or we could show the same way side equals side congruence criterion, and then just view BD as a transversal of AD and BC, and we'd see that the alternate interior angles are equal, and therefore we have a parallelogram there.
William again back with the lemma. So we've just shown that the quadrilateral XYRP is a parallelogram. So that means that XY is parallel to BC, which is what we were trying to prove with this lemma. Not necessarily this entire presentation, but it's an important point. Alternatively, we can say that if XY was parallel to BC from the beginning, then we can say that the two triangles were similar. So we can finally move on with trying to prove our original theorem about the centroid and the concurrence of the medians. Finally, coming back to our original theorem about the centroid, using the lemma that we just proved, we can finally say that the two triangles are similar since xy is parallel to BC, so you get that the two angles GXY and GCB are equal, and the angles XGY and CGB are equal. So through angle-angle criteria, we get two similar triangles, and so we get that sort of algebraic definition of similarity that we introduced previously. But it's not enough to say that the two triangles are similar. We need to prove that the centroid lies 2/3 of the way along a median. And how do we get that number 2/3? Well, that's shown through a different theorem called a corollary. This corollary is based off of the discussion we had earlier about our lemma. So when you have a medial line, again, that is a line connecting two midpoints of two sides of a triangle, you can show that the two triangles formed are similar by a ratio of 1/2. So you can see that AX over AB is equal to 1/2, which is also the length of, which is also the ratio of AY over AC. So the two triangles are similar. So it also follows that XY is equal to 1/2 BC. And so that's all this corollary is trying to say, that when you have a medial line, it is equal to half the length of the corresponding line of the original triangle. So we now know that xy is equal to half the length of BC. And since the two triangles are similar, we can say that xy over BC is equal to 1/2, which is equal to gy over bg. So then gy is equal to 1/2 bg, and by is equal to bg plus gy, which, given what we said earlier, is equal to bg plus 1/2 bg. So by is equal to 3/2 bg. So then bg is equal to 2/3 by, and it's similar for cx. So what we've just shown here is that the point G is 2/3 along the way of the median by from the point from the vertex B. So we've discussed where the point G lies on a median, but how do we show that all of the medians intersect concurrently at this point G? How do we prove that? Well, what we had just shown, if we look at the two medians by and az, we similarly get that the point G prime divides these medians into 2/3, where the point G prime is 2/3 along the way of by and 2/3 along the way of az. This is going through a similar process to what we did to show by and cx. But the point G in our theorem also lies 2/3 along the way of the median by. So that would mean that the points G and G prime are concurrent. And this can similarly be shown with looking at the medians AZ and CX, that they also lie on point G, which means that the point G is the intersection for all three medians, and we call this point the centroid. So what we have just shown today is the definition of a centroid being the intersection of the three medians of a triangle, and that the centroid lies 2/3 along the way of a median from the vertex. This has been our first draft. Thank you all for listening.